Hi, in this video I will describe a general result on non-asymptotic bounds for forward processes in denoising diffusions and discuss key elements of its proof. We start with a probabilistic problem. We have two processes, Ornstein-Uhlenbeck process with standard normal invariant measure started at some multimodal data distribution, and a general diffusion process with a possibly different invariant measure started at the same multimodal data distribution. The problem is very simple now. We want to compare the convergence rates to stationarity of these two processes. For better visualization, on the left we see a typical multimodal spread out data distribution where we start from, and on the right we see a typical invariant measure which is structureless, centered, and unimodal. Now, for more context on how this probabilistic question is related to denoising diffusion probabilistic models, see part 1 of this presentation. In order to say something about such probabilistic problem, we need to impose some rigorous assumptions on the data distribution in the forward process. Data distributions that appear in practice are known to be highly multimodal, and thus we parameterize the data distributions here by the distance of their furthest node from the origin, and this distance we denote by r. B rho in this case is the mass that the initial distribution charges to this node, and because this is the furthest node from the origin, the initial distribution charges very little mass further away. And this would be an example, multimodal. This is a heat map of a multimodal distribution. It has a furthest node, and it charges very little mass for the points that are further away. And note that we haven't assumed, made any assumptions on moments, log concavity, density, or any other assumptions that are convenient in probabilistic language, because we want to capture distributions, general distributions that appear in practice and might violate these assumptions. And also this assumption allows for manifold hypothesis, which states that the real-world complex data lives on a submanifold of a Euclidean space with possibly very high codimension. The second assumption we need to make is on the forward process. General ergodic diffusions are too large of a class to be analyzed directly, and also are not that relevant for applications. So the first assumption we make is on the drift of the diffusion, and we assume that it exhibits at most linear growth in each direction. This is a natural assumption because diffusions with superlinearly growing drifts are known to be difficult to sample from. The second assumption is more subtle and technical, and it's made on the instantaneous variance sigma of this diffusion. We assume that for some k-dimensional projection, which has one arbitrary element, this dispersion coefficient equal to sigma transpose will be balanced across all directions in this projection of this k-dimensional projection. And this might be difficult to grasp at the first glance. So let's see an example which satisfies this condition. If we have a dispersion coefficient where the state dependence is only in the scalar part, only appears as a scalar function, then this technical condition 1 will hold for all three and more dimensional projections. So this can be viewed as a generalization of a tempered Langevin class. And now we can state our main result, but the last quantity we need, which will play an important role here, is the epsilon quantile of this k-dimensional projection on the invariant measure pi. So this epsilon quantile will be important for our result. In our main result, we start with the data distribution which has a furthest node at a distance r from the origin, And if we look at this terminal time, that is a ratio, that is a logarithm of the ratio between r and 2rk, at this time, no diffusion in this very large class will be close to its invariant measure. You see? And on the other hand, if we increase the time horizon to a maximum of 2 times, which is definitely larger than Tc, because it's larger than logarithm of r when r is the distance to the furthest mode, then the Ornstein-Uhlenbeck process will converge. So this is a very general result that gives some bounds on convergences of large class of diffusions. But this generality makes it difficult makes it in some sense uninformative. So to put this general result in the context of the denoising diffusion probabilistic models, we impose some additional assumptions which prescribe a relationship between these crucial quantities which are relevant in the context of these algorithms. And our assumption takes the following form. In the first part, we assume that the distance to the furthest mode exceeds the square root of error tolerance epsilon times dimension to one quarter. And this is a very mild and natural assumption. The distance to the furthest mode in a lot of data sets, such as image data sets, will grow as a square root of a dimension. And for some other data sets, it might even grow faster. And on the other hand, this is dimension to one quarter multiplied by error tolerance, which is known to be very small. So this is the mild assumption that we should always hold. The second and third assumption are a bit more subtle. So we assume that the distance to the furthest mode is considerably larger than this quantity on the right, which depends on the radius of the furthest mode, which is expected to be tiny with respect to the distance to the furthest mode. So this is not a strong assumption, but the quantity that makes this guy large is 1 over epsilon. So we divide this quantity by epsilon, and the error tolerance is small, which makes this large. However, the error tolerance is fixed in dimension, and the distance to the furthest mode grows in dimension. So when we consider larger and larger data sets, this beta can be chosen smaller and smaller. And because relevant data sets are extremely large, more than million dimensional, this beta can be chosen sufficiently small and not too large. And the last assumption is related to this epsilon quantile of the k-dimensional projection, and on the invariant measure pi. And because these relevant invariant measures extend the Gaussian class, those measures are centered, unimodal, and light-tailed. And in this case, these k-dimensional, quantiles of k-dimensional projections will not grow significantly in dimension. For the most distributions, such as normal distribution, this quantile of k-dimensional projection will be fixed in dimension. And for some other distributions, it might grow logarithmically in dimension. On the other hand, distance to the furthest mode grows polynomially in dimension, which means that this condition should be satisfied with beta small when we consider very high dimensional data sets. And now, since we put these key quantities in the context of denoising diffusions, let's see how our main theorem looks in this context. So again, we start with the data distribution, which has the furthest mode at a distance capital R. And if we consider time horizon that's slightly less than logarithm of R, then every diffusion in this large class will fail to converge. We're going to have a decently large error in total variation. But if we slightly increase this time horizon to slightly more than log of r, then Ornstein-Uhlenbeck process will be very close to converging. The TV distance will be less than epsilon. And this result conveys the most important message that we're trying to give here, which is that in this context, Ornstein-Uhlenbeck process is hard to beat, as slightly decreasing the time horizon at which OU is essentially converges up to epsilon means that any other process will fail to converge. So OU in this context is hard to beat. So this is our main result, and now I'd like to dedicate the rest of this presentation to talk about some key elements of its proof. We start again with the first picture. We want to transform the multimodal data distribution in unimodal structureless invariant measure, and we want to get some bounds on the convergence of this procedure. And what we really want in this case is we want to obtain bounds under minimal assumptions on rho 0 and the process y, because we really want to consider a large family of processes and data distributions that appear in practice. And at the same time, we require non-asymptotic bounds on the convergence rate, because we compare what happens to the marginals at fixed times. So constants are crucial here. And these two, minimal assumptions and non-asymptotic bounds, are often non-compatible, because in general theory for non-asymptotic bounds on the convergence, because this general theory of non-asymptotic bounds on the convergence rates of Markov processes often requires heavy analytical machinery, such as Poincare inequalities, which require a lot more structure. But in the context of this problem, we avoid this issue completely by focusing on the structure of the problem, and in particular on the bottleneck for the rate of convergence, which is transforming the mass from furthest mode or furthest modes towards the origin where the invariant measure charges most of its mass. Most of the mass of the invariant distribution lies. And the inspiration for this approach comes from the idea of Martin Heidegger, who studied some hypoelliptic systems that arise in mathematical physics. And he noticed that if a process, diffusion process, admits a heavy-tailed invariant measure, then a sharp lower bounds can be found if you look at its tails and the difference between the mass that invariant measure charges to its tail and the marginal charges to its tail. So really the bottleneck is that the process does not move sufficient amount of mass to its tails, which makes the convergence slow. And in our case, we have a reverse situation. We have a light-tailed centered invariant measure, but highly multimodal spread out initial condition. And the natural candidate for a lower bound in this context is a difference between the mass that the invariant measure charges near the origin and the amount of mass that the process has managed to send to the origin from its multimodal initial condition. And in order to use this idea, we prove this lemma that holds for general Markov processes. And so we are given a Markov process with a generator, and we have some Lyapunov function that maps Euclidean space to a 0-1 interval. And we assume that we have some bound on this generator. And then the lower bound on the total variation distance between the marginal and pi takes the following form. The first element in this lower bound is positive, is the amount of mass that the invariant measure charges a compact set that charges a level set of H, and then we subtract the amount of mass that the initial condition charges to a slightly larger level set of H, and then additionally we subtract the amount of mass that the process manages to send towards the desired level set, to transform towards the desired level set up to time t. And this is our formula for the lower bound on the total variation distance. And it's a starting point for our approach. So we have this general formula, and now, in order to make it work, we need to find the suitable Lyapunov function. And a natural choice, because we assume that the bottleneck will be in the set centered around the origin, is the function of the norm. And yes, so the function of the norm. And so if you consider some very centered light-tailed invariant measure, this such level set will capture most of its mass, which will make this first element in the lower bound very large, which is very good for us. But the problem is that while this works really well with a really small with a set with very small support, in low dimensions, it doesn't work so well in a high dimensional setting. And the problem is that if you want to consider a set that captures most of the mass of pi, where pi is, let's say, Gaussian distribution, you need to increase the radius of this set with the dimension, which means that these sets have to be enormous when you're working with a dimension more than 1 million. And that no longer makes this approach efficient, and because the lower bound is no longer, the lower bound that can be obtained here is no longer sharp. But this has a very natural solution given how the real world data looks like, and that is a projection to a critical submanifold. So recall the manifold hypothesis, which states that a real world data lives on a submanifold of Euclidean space of a very high codimension. So instead of considering just a function of a norm, we should look at the function of a norm of a projection to the critical submanifold where this data actually, where the critical data actually resides. And in our case, this critical data will be the critical mode that's furthest away from the origin. And so we choose this mode that's furthest away from the origin, and we consider a k-dimensional projection which to the space, which includes this direction towards the furthest mode. And we know from the assumption of the forward process that such projection, that we can choose such a projection, that on this projection, this dispersion coefficient is sufficiently balanced and our diffusion behaves in a suitably nice way. And then you can, once we choose such a projection, we get our Lyapunov function, which is not a function of a norm, but function of a norm of this projection. And also because have this nice behavior of dispersion, we also get a bound on the generator applied to this projection. And these are the key elements. From these elements, we can then directly get our result by just plugging in key parameters. The first one would be the epsilon quantile, which captures most of the mass of pi, and the other one would be the distance to the furthest mode from the origin. So for sufficiently small times, which depend on this distance and this quantile, every diffusion process that we consider in this context will fail to converge to stationarity. On the other hand, to get upper bounds on the convergence of the OU process, this is an easier and more direct task because explicit densities of OU are known, and we just use these densities in Pinsker's inequality. And yes, these are the key elements of our proof that I wanted to emphasize. To conclude, I'll just mention again that this is a robust, self-contained approach and can be applicable in a more general setting. One thing to mention is that the lemma that I've described has nothing to do with denoising diffusions and can be applied to a general Markov process, might be interesting in other contexts. And we provide here lower bounds for the convergence of the general forward process. But this problem of lower bounds and bounds in general for the reverse process in full algorithm still remain open in some sense. We still haven't tackled them, and this is something that we would like to do in the future. And thank you so much for your attention. And here there are some sources that have inspired our work.